Now that we've talked a lot about the inverse, let's look at some of the basic properties of the inverse in invertible matrices. The first property we'll look at, let A be an n by n matrix. If B is also an n by n matrix, satisfying either BA is equal to the identity or AB is equal to the identity, then B is equal to A inverse. The main thing about this one, before when we wanted to check if a matrix was an inverse, we had to check A times B as well as B times A. And this says as long as one of them works, we have the results. So let's try to prove this. Let's suppose that BA is equal to the identity, and we have a system of equations AX equal to 0. We can multiply on the left-hand side by B to get B times AX is equal to B times the vector 0. Since B times A is the identity, the left-hand side would simplify to just X, and anything times 0 is 0, so the right-hand side would simplify to 0. So we have that X is equal to 0. So now I have a homogeneous system, AX equal to 0, that has exactly one solution, X equal to 0. So we know that A is invertible. So if BA is equal to the identity, we do have that A is invertible. Since we know that BA is equal to the identity, I can multiply on the left by A and on the right by A inverse. Since the left-hand side had an A times A inverse, I can simplify that down to just AB, and the right-hand side will simplify down as I. So I've shown that we also do have to have the other direction. If BA is equal to I, then we must also have that A times B is equal to I. And this is only half the proof. We also need to suppose if AB is equal to I and show that, once again, A is invertible and that BA is equal to the identity, but it follows from this same basic idea. Our next result, let's let A and B be n by n matrices. If A times B is invertible, then A and B must also be invertible. So if the product is invertible, then each of the pieces must also be invertible. We're going to start by defining C to be equal to B times AB inverse and D to be equal to AB inverse times A. Multiplying the first of these on the left by A gives me AC is equal to AB times AB inverse. Multiplying the second one on the right by B gives me DB is equal to AB inverse times AB. The right-hand side on both of these just simplifies to the identity, so I have that AC is equal to I and DB is equal to I. And by the theorem that we just proved, that's enough. It tells us that not only are A, B invertible, A inverse is equal to C and B inverse is equal to D. So there we have it. My next result actually looks at the inverse of a product. So if A and B are n by n invertible matrices, then the inverse of AB is equal to B inverse times A inverse. So we need to be able to multiply AB by this thing that we're claiming is the inverse, B inverse, A inverse, and we should be able to get back to the identity. Using the associative property of multiplication, I can regroup this to be A times BB inverse times A inverse. B times B inverse is just the identity. And multiplying by the inverse doesn't change anything, so now I have A inverse, which once again simplifies to the identity. And that's enough. Show that I multiply AB by the thing that I want to be its inverse and get the identity. Therefore, it must be the inverse. This time I'm going to let A be an invertible matrix and N be a non-negative integer. And I'm going to state a couple of different properties about this. The first, if A is invertible, then A inverse is also invertible, and the inverse of the inverse is back to A. The second one, A to the nth power, where once again N is a non-negative integer, will also be invertible, and the inverse of A to the N is the same thing as A inverse to the nth power. My next one, RA is invertible, where R is a non-zero scalar, and the inverse of RA is R inverse A inverse. And then we have that A transpose is invertible, and the inverse of the transpose is the same thing as the transpose of the inverse. While I won't prove any of these, I highly encourage you to try to prove them yourselves.